Okay, so we're going to do, it's the same assignment, because the point of these questions is just to get you to go through them, understand them, practice them. That's the real reason for it. It's not so much for marks. So it's from last year, this year's 2019, making this. We did question 1. So question 2. So we're given, and let me see if I can adjust this a bit. Calculate the standard knot entropy at 298 Kelvin for copper. So we know that the back of the book, they end up giving you absolute values of entropy, and the knot stands for 1 bar, and the back of the book is 25 degrees Celsius. So fair enough. We're supposed to use this data collected of copper, and the data looks like at different temperatures they have measured the heat capacity, and the subscript P means they've experimentally recorded the heat capacity at constant pressure. We know that heat capacities, and one of the ideas is the generic heat capacity is sort of this idea of, a quantity of heat, and then you watch the change in the temperature. So to generate heat capacities, you basically watch what the heat does in the temperature, and it's the slope of the graph. So the interesting thing is there's 2 extremes, popular 2 extremes. Constant volume heat capacity. So for that experiment, you have a steel box, and you put in some heat, watch what the temperature does, get the graph. The slope is the heat capacity. If you conducted the experiment at constant volume, it gets a subscript V. If you did it at constant pressure, the classic simple example is a piston, and let's just say that it was, for instance, 1 atmosphere pressure only. So when you heat this sample against a constant pressure, watch what the temperature does, you'll get a different heat capacity, a different slope. So 2 sort of well-defined experimental processes. And any generic C could be anywhere between this, depending on the process you've chosen to do. So maybe there's an industrial process or something like that, where both volume and or pressure could be changing as the process continues. So you would have to experimentally run the process and record the temperature changing to heat added to get a specific heat capacity. So that just kind of tidies up the idea. This could have been CVs, and you could still do this calculation because you'd be calculating the entropy under those conditions, if you will. So we'll come back to that after and get but the long story short, this is the data you're given. So what we know by definition of entropy, one of the definitions was the change in entropy is simply related to the amount of heat, right, transferred at a given temperature, so to speak. Now the interesting thing here is we know that dQ comes from heat capacity related formulas. One way of doing it would be the change in heat, if the process was constant pressure, would be Cp dt. So in place of dQ, we could put Cp dt in place of that, which looks like this, divided by the actual temperature of the moment, if you will. Or dQ, if the process was constant volume, would be CVs. So we talked about that briefly, but you can see how if what we're doing is a constant pressure process, the entropy will be related to this. So when we go to integrate this, you get delta S, and we'd have to integrate this side just like this. So one of the things I'm going to talk about over here is to graphically get an answer for the entropy between 2 values, which in our case, calculate the absolute value of entropy at 298. So what they're basically saying is whatever the entropy was initially, which was 0 Kelvin, all the way up to 298. So you're going to somehow integrate and get the area under some kind of graph from 0 to 298. That will give us the value of entropy for copper at 298. So the limits of that integral will be basically from 0 to 298. So we have to graph Cp over T against temperature. So we go back to physics just to recall, and this is one of the tricks to remind yourself for other things you're unfamiliar with. When you have a differential equation and you're going to integrate it, the rule is whatever is between the integral sign and the changing variable, this will become your x-axis, whatever's right there, right? And what's between this and the integral, this is your y-axis value. So one of the ways to demonstrate that to yourself is if you go back to physics and you look at, for example, what if you had velocity versus time graph? And let's just say that the accelerate, because the slope of this is acceleration. So the classic thing, like the force of gravity is constant, acceleration is constant, you get the straight line for velocity versus time. We know that dx dt equals the velocity as a function of time. So we could bring the dt over here, and when you integrate this, so velocity will be the slope of a distance time graph, but when you have velocity as a function of time, which means velocity on the y-axis versus time, you get this equation of that line. You can rearrange the dt over here, and you can say, okay, if I integrate this, you would get delta x, which is what is the change in displacement of something between these two times. You integrate this side, and we know that you have to put between this integral and dt, this is your x-axis, time. This has to be your y-axis thing. I need data on what the velocity is doing as a function of time. So if somebody said, go ahead and tell me how to graphically get the change in displacement of an object, guess what? It's the area between these two times of a graph of vt versus t. That area will be that. So this is a demonstration that talks about when you get to this point, what's between the integral sign and the changing variable here. That's your y. So what we're going to do is we're going to find the area under for our entropy. We're going to graph Cp divided by T on the y versus T. And then we're going to break it up. So what it looks like is, I didn't reprint this, so you can see it's kind of, I've used this for a few years. This is the overall graph, so you can see from 0 right up to 300. The actual, I didn't even, this is really grossly drawn. It'd be a nice curved line. So this is the graph of Cp divided by T versus T. I chose to break it up into, I think, 3 points. I think I chose this point right here, which was 30. So this piece, I put it on one graph, and all you're interested in is the area under this experimental data points up to 298. So you want the area under that. So you break it up into pieces. I went 0 to 30, probably, I'm looking now, fit it with a quadratic to find the area under that piece. Then the next piece, I fit it with something, probably a quadratic to find that. And then even the third piece, I did the same thing. And then you add up the 3 areas, and that's basically your answer. But just to give you an idea, that first piece, 0 to 30, you can see I graphed that, and it fit in Excel very well. So you can take this right there, equation, and you find the area under it. So all it means is you take what Excel gave you, ax squared minus bx plus c. That should be plus. So whatever the values of a, b, and c are, and you can clearly see here, there's your a value. This becomes your b value. This one has a negative, and that's your c value. So do you see what I did? I just went ahead and said I'm going to integrate this, and I'm going to get the generic form, right? A x cubed blah blah blah, and I'm going to integrate it from 0 to 30. So you can see how you can integrate this between 0 to 30, and this is what you get. And then I put in my value of a at this point to calculate a number. So this is the area, and the units is always. The units come down to, when you look at the area under this curve, right? If you look at a piece of a rectangle, your x-axis is in Kelvin, and this rise is over here, which is Cp, which has units of joules per K per mole divided by temperature. So when you multiply these two together, you end up getting joules per K per mole, which is what you're supposed to get for entropy. So that's piece number one. Piece number two, I opted to go from where I left off at 30 up to 75, and for some reason it fits so nicely. So I get another quadratic, I integrate that, so I got the area right there under that curve. And then the final one, I ended up fitting it with, and you can see the one spot here is a little bit out. So this isn't, you know, I could have arguably broke it up into further smaller pieces, but this was 0.99, so that's okay. So it's a cubic, so I integrated that one to find the area under here. You add it all up. So basically, I'm not so worried about basically almost giving you the answer, but the number you're looking for, let's just say that your final number for the entropy of copper, which is 0 up to 298, you're looking for a number that's somewhere between 30 and 35 joules per K per mole. Notice I'm saying somewhere, so I'm giving you a ballpark range. So if you get a final answer that's not within this range, then chances are something went wrong. So this is mainly an exercise to go through what in industry or other places you sometimes have to do. So that's how you do question 2.